Let's take a look at problems 6, 7, and 8 on the Uniform Circular Motion problem review sheet. Number 6, a child is twirling a 0.012 kilogram ball on a string in a horizontal circle whose radius is 0.1 meters. A horizontal circle is like you're swinging it over your head like a lasso. The ball travels once around the circle in half a second. We're going to find the centripetal force acting on the ball. Now, what happens if we double the speed? Does the centripetal force double? If not, by what factor does it go up? Does that mean is it 4 times bigger, 8 times bigger, only a half bigger? So what would we do there with number 6? So first things first, I write down all my numbers. My mass is 0.012 kilograms. My radius was 0.1 meters, and my time was half a second, and we're trying to find the centripetal force. So I look at my equation sheet and say, what equation should I use that has centripetal force and these variables? I picked centripetal force equals m4 pi squared r over t squared. I can plug in my numbers. We know the mass was 0.012 kilograms, 4 pi squared, and the radius of 0.1 meters, all divided by the time, 0.5. Don't forget to square it. I plug in all my numbers, and I get a centripetal force of 0.19 newtons. What happens if we double the speed? Well, if we double the speed, it's going to take half as long to go around. Twice as fast, half as long. And that means that my time is now 0.25 seconds. My equation is exactly the same because my mass is unchanged, my radius is unchanged, and I still have time. I just have a smaller time as 0.25. And that means my numerator is the same, 0.012 kilograms for my mass, 4 pi squared, and my r is 0.1 meters. But now I'm dividing by 0.25 seconds, and again, don't forget to square it. When I do that, I get a centripetal force of 0.76 newtons, which is 4 times larger. Why is that? That's because when I cut my time in half, I'm squaring that. And that turns it into a factor of 4, not a factor of 2. So my centripetal force gets 4 times bigger. So if you want to go twice as fast around a turn, you don't need twice as much force. You need 4 times as much force, which is why speeding around turns is not a great idea. Now let's move on to number 7. Number 7, a 0.015 kilogram ball is shot from a plunger of a pinball machine and follows a circular track with a radius of 0.25 meters. The ball experiences a centripetal force of 0.028 newtons while traveling that circular track. So what is the speed of the ball? Going to our list of things we were given, the mass is 0.015 kilograms, the radius is 0.25 meters, and the centripetal force is 0.028 newtons. We're looking for the velocity. So I'm going to take a look and say, well, what equation can I use? It's going to be one of my centripetal force equations because that's a variable that I have. And I'm going to pick the mv squared over r version because I have m, I have r, I have f of c, and I want v, so it better have v in it for me to get this. Rearranging this equation, I multiply r up to the left, which is why centripetal force and r are in my numerator. I'm going to divide mass out because it's being multiplied by v squared. That's why it's now in the denominator. And to get rid of my squared next to the v, I have to take the square root. Plugging in my numbers. Centripetal force was 0.028 newtons. The radius was 0.25 meters. The mass 0.015 kilograms. And I get a speed of this ball of 0.68 meters per second. That's how fast the ball is going around this little track. Number 8, which is a starred problem, a little bit more challenging. There's a block and it's hung from a string inside the roof of a van. The van's going straight ahead at a speed of 32 meters per second, and the block just hangs vertically downward. But if the van maintains that same speed but goes around a turn, which it has a radius of 130 meters, the block swings toward the outside of the curve. Then the string makes an angle with the vertical. We're going to find that angle. And there's usually a theta here. Not sure where that went when I converted to Google Docs. I'll have to put that back in there. But we're going to find that unknown angle. Now, if you have anything on a string, your keys, whatever, you can just hold it in your hands and you'll see that it just hangs straight down. But start to spin around and you'll notice that the string is going to go outward with your keys here, and it's going to go toward the outside of the turn. Anytime you make a turn, that will happen. So the velocity we're given is 32 meters per second. The radius is 130 meters, and we are looking for the angle. We don't have an equation in our uniform circular motion equations which has an angle in it. This is what makes this a little bit more challenging. So we have to go to what do we know? And whenever you're not sure, it's always a good idea to draw the picture. So here's the little weight, here's the string, and here are all the forces acting on it. Gravity pulls down, and the string pulls up and at an angle. Well, any force is up and at an angle, I'm going to break into its components. The tension in the x direction is going toward the inside of the turn. This would be like if we were behind the van and it's making a right turn, you'd see the block swing toward the outside of the turn. So this tension in the x is pointing towards the inside of the turn, and tension in the y direction is pulling up. Well, we know that the upward part of tension is going to equal the downward part of gravity, or force of gravity, because it's not accelerating up and down. So that was the old forces stuff. Up stuff equals down stuff. And I have that right here. Tension in the y equals force of gravity. And any force that points towards the center of a circle, in this case that's Tx, is my centripetal force. So that's why I said the Tx is what's allowing this block to go in a turn. If we just suddenly snapped a string, the block would go flying off to the outside of the turn. So the Tx is what's allowing this to happen. So I'm going to do a little bit of geometry on this. By the way, these are the exact same things as what happened in the flying pig lab, where the tension up equal gravity and tension in the x equals centripetal force. Now, tension in the x is the opposite side of my triangle, so I'm going to use sine for that, which is why I said sine of theta, this unknown angle, times the tension itself is Tx. So that's where this comes from. Tx is the side of the angle times t. And centripetal force, I'm going to use mv squared over r, because I have r and I have v, so it makes sense to use the one I know the most stuff in, which is mv squared over r. T in the y equals force of gravity, and t in the y is the adjacent side. So that's the cosine of the angle times tension. So that's just ty from a little bit of geometry. And force of gravity down is m times g. I'm going to divide these two equations. So I have sine of theta over cosine of theta, t over t, and the t's are going to cancel. And sine of theta over cosine of theta is tangent of theta. So I just did this division and put it right down here. I divide these two guys, because this is a simultaneous equation, which I'm allowed to divide these two things. So mv squared over r divided by mg, the m's cancel, leaving me with v squared in the top, and the r and the g hang out in the bottom. So tangent of theta equals v squared over r. I'm trying to solve for theta, so I'm going to get rid of the tangent by doing the inverse tangent to the other side. And that gives me theta equals the inverse tangent of v squared over rg. Plugging in my numbers, v was 32 meters per second. Don't forget to square it. Divided by r and g. R is still 130 meters. G is always 9.8 meters per second squared. When I plug all that into my calculator, I get an angle of 38.8 degrees.